A mover is dragging a box full of electronics from the house to a moving truck. He is pulling on a rope with a 400 Newton force. The rope makes an angle of 64 degrees with the vertical as shown. In the picture to the right, the box is moving at a constant velocity. The coefficient of friction is 0.560. What is the weight of the box? So to begin this problem, I'm going to start with a free body diagram. So let's see, I'll start with this. Here's my free body diagram, just a dot. That's the actual body, which is the box. And when I look at it, the box has weight going down, so that's going to be weight. And I'm going to use mg to represent weight. Because the box is on a surface, the surface is going to exert a normal force against the box. So there's the normal force acting against the box. And it says there's friction. Friction cannot generate like the motion. So the motion is going to be going to the right where it's being pulled. Friction is going to oppose that motion, so the friction is going to go to the left. And then to the right, I've got this rope or whatever it is pulling at my 64-degree angle. And everything is moving at a constant velocity. There's the 64 degrees. Since it's moving at a constant velocity, there's not going to be a net acceleration. So there's my free body diagram to begin with. But because the tension is not perpendicular to any of the other forces, I need to draw a second free body diagram. And on the second free body diagram, I'm going to take the tension and break it up into its horizontal and vertical components. Or in other words, components that are going to be parallel and perpendicular to the other components that are here. Oops, I forgot to label the friction. There's friction right there with the cursive F. Alright, so down here, let's go with another free body diagram. Normal force, just copy it over. Friction, just copy it over. And label it this time. mg goes down, just copying that over. That's the weight, remember. And the tension, I'll copy that over. So here's the tension, T. If this was my piece of paper, I'd draw these free bodies bigger, but I'm limited to my screen size. So here we go. Next step, I need to take this T and make it the hypotenuse of a triangle. Now remember, let's see, that's 64 degrees. So I'm going to draw my triangle around the angle. So it's going to go up and over. And this triangle is not just a triangle, these are vectors. These are horizontal and vertical components of the tension. So I have to add up the vectors to give me this tension, which means the two tips have to meet. And then when I draw the bottom piece, it's got to meet tip to tail so the two components can connect according to our rules of addition for vectors. So that's all set. Now I need to label these sides. So when I label them, I'm looking at my trig functions. I know that the horizontal vector in this case is opposite the 64, so I'm going to use the sine function. If I look at my trig, I know that I'm going to have, let's see if I write it down here, sine 64 is equal to the opposite side, which I'm looking for. I'll just call it OPP, opposite, and the hypotenuse, which is the tension. So the opposite side is going to be T times sine 54. So up here, I'll write T sine 64. I think I just said 54 by accident. For the vertical side, I'm going to use the cosine function. So cosine 64, and that's going to equal the adjacent side divided by the hypotenuse, which is the tension. So the adjacent side is equal to T times cosine 64. So over here, I'll write T cosine 64. All right, now that I have those two sides done, one of the things that I'm going to do is I'm actually going to ignore the T and the hypotenuse in any of my math calculations. Oops, my screen's moving all over the place here. So I'm not going to do anything with that, and I'm not going to do anything with that in my summations. And that's because my two horizontal and vertical components, they equal, according to vector addition, the tension at that angle. Okay, so let's start summing up everything. Sum of the forces in the x direction equals, well, it's not changing speed in the x direction, so I'm going to make that equal to 0. And that's going to be, in this case, all the forces going in one direction minus the other forces going the other direction. So I'm going to choose all the forces going to the right minus all the forces going to the left. So that's going to be T sine 64 degrees minus a cursive F, which is my symbol for friction. And then I'll do, let's see, so that's going to give me the equation. 0 is equal to T sine 64 degrees minus friction. And then I can sum up the forces in the y direction. Sigma Fy equals 0 again, because it's not changing speed in the vertical direction. And that's going to equal, and I'm going to make it all the forces going up minus the forces going down. And I've got two forces going up. I have eta and t cosine 64. So that's eta plus t cosine 64 minus the forces going down, which is the weight. And I'm using the symbol mg for the weight. All right, so that's looking good. And that's going to give me the equation 0 is equal to eta plus t cosine 64 degrees minus mg. At this point, I've got two equations and way too many unknowns. So I need to get rid of them. To do that, I'm going to start using some substitution. And whenever I have friction, one of the key things I can go for is the definition of friction. Friction is equal to mu times eta. So what I can do is I can take this expression of mu times eta and replace this f with it. And that'll rewrite this as 0 is equal to t sine 64 minus mu times eta. So I got rid of friction, which is one of the unknowns. The other unknown I have is eta. So now I need to get rid of that. So to do that, what I'll do is I'll go to the other equation, which is going to be right here. So I'll go to that equation, and I'm going to isolate eta. So now eta is equal to, well, I need to put mg on the other side, so negative mg, when I move to the other side, becomes positive mg. And to move the t cosine 64, I got to subtract it from both sides. So it's minus t cosine 64 degrees. Awesome. Now what I'm going to do is I'm going to take this whole expression on this side and put it in for eta in the previous equation. So 0 is equal to t sine 64 minus mu times parentheses mg minus t cosine 64 parentheses. Okay, so I'm looking for the weight in this problem, the weight of all this. And I know that weight is equal to mg. So really what I'm looking for is to put mg on one side of the equal sign. In other words, this mg right here. So to do that, the first step is I've got to distribute the mu in the parentheses. This will be 0 is equal to t minus sine 64 minus mu times mg plus mu t cosine 64. So I had to take mu, multiply it by mg, and take the mu and multiply it by negative t cosine 64. So that wasn't just mu, that was actually negative mu. So negative mu times mg and negative mu times negative t cosine 64. Now I've got to take my mu mg and bring it over to the side of the equal sign all by itself so I can isolate it. So I'm just going to move it over by adding it to both sides. So that'll be mu mg, and that equals everything that's left. T sine 64 plus, where'd that minus come from? Oh, that's just like a mental typo there. There's no minus. There's no minus. Okay, so t sine 64 plus mu t cosine 64. Now the goal is to isolate mg all by itself, so I'm going to divide both sides by mu. So if I do that, this becomes mg equals t sine 64 degrees plus mu t cosine 64 degrees divided by mu. And now just put in the numbers, and that'll give me the weight, because remember, mg is the weight. So mg is equal to tension, 400 newtons, sine 64 degrees, plus mu, which is 0.560, no units, times tension again, 400 newtons, cosine 64, divided by the coefficient of friction, 0.560. After doing the math, I can see that mg is equal to 800 817 newtons. Since the weight equals 817 newtons, I know that's the answer to the question. The weight is equal to 817 newtons.